All right, good afternoon. No, what's going on in Texas right now? I stopped watching the news a while ago. Deep freeze or something, that's probably not good. Yeah, hope everybody had a good weekend. Hopefully you got to enjoy the snow and didn't have to deal with power outages and stuff. Igloo-like shelters, cool. I grew up in New York State, so especially when I was a kid, snowfall was a huge deal, and it would often be over my head, and my brother and I would go out back and we'd dig tunnels, that you could actually like run around in without the other people seeing you, and we'd make snow forts and things like that. And if you're gonna have snow, it's nice to be able to enjoy it. Um, but yeah, losing power is not good. Alrighty, so I posted programming assignment 1, which is a problem related to Goldbach's conjecture, which we talked about briefly when we were doing number theory. So let me start by running through this. And then I want to go through the midterm, and then we can talk about homework questions. Actually, I'll do homework questions first, and then we'll run through the midterm, and then we'll go on with induction. Yeah, thunderstorms will do that for sure. I lived in North Carolina, and it was the first time I realized that like weather could be like deadly. Because New York, it snowed and stuff like that, but people didn't like, suffer grave harm from snow. In North Carolina, tornadoes was a different story. But I love North Carolina. Cool, East Coast contingent. Alright, so programming assignment 1. You are writing a program to demonstrate Goldbach's conjecture. So let's recall what Goldbach's conjecture is. Basically, you take an even number, you can write it as a sum of two primes. So I can write 10 as 3 plus 7. I can write 12 as 5 plus 7. I can write 14 as 7 plus 7. I can also write it as 11 plus 3. Or, of course, 3 plus 11. So generally, there are a lot of ways we can write even numbers as a sum of two primes. The conjecture is simply that there's always at least one way to do this. And this is for numbers 4 or bigger. And so your goal for your programming assignment is to write a piece of code that demonstrates this. So let's look at the specifics. So ask the user to enter a starting number, and ask them to enter how many numbers they want to check. Okay, and I'm not worried about like syntax checking on this. We're interested in the behavior of the code as far as Goldbach's conjecture. So, ask them for two integers. First is the number that they want to start from, which should be even. The second one is how many numbers they want to check. And then try to find a right way to write each of those numbers as a sum of two primes. All right, so start with the first number. If you can write it as a sum of two primes, add 2 to it, try to write that number. Add another 2, try to write that number, and keep going until you've done however many numbers they wanted you to check. And you should be able to always do this. If there's a counterexample to Goldbach, it's a huge number, bigger than what we could reasonably check with 32-bit integers. All right. So your submission for this assignment is going to be a single PDF file containing two things. The first is a copy of your source code. Right? So print it out, in a document, and then append to it the output you get for running your program trying to demonstrate this conjecture for 500 even numbers starting from 5 million. So numbers from 5 million up to 5,998,000. And so you should have, 500 lines of output that look like this, starting with 5 million equals, 5 million and 2 equals, 5 million and 4 equals, and so on. All right. So some notes and suggestions to get you going on this if you haven't already done it. So write a function that tests a single number to see if it's prime, right? And you can do this just by exhaustive division. How do you know if n is prime? See if you can divide it by 2, 3, 4, 5, 6, and so on. Up to and including the square root of the number. You got to include the square root. But you don't have to go all the way up to n minus 1. And in fact, if you try to do that, your program will not finish when you try to run it on numbers around 5 million. Well, it'll finish, but it'll take a long time. And if you want to be a little quicker, make sure your number is not even. If it is, then it's not prime unless it's 2. Otherwise, you only have to test odd numbers. So from 3 up to and including the square root of n. And you don't have to actually divide. You can use the modulus operator in C. And if a modulo b is 0, then a is divisible by b. So that's a useful operator for checking to see if one thing's divisible by another. And then here's a really important point about designing your algorithm. So here's a quick way to do this. So let's say we want to try to write n as a sum of 2 primes. Alright, here's how I can do this. So it's prime if a is not divisible by b. If it's not divisible by anything other than a and 1, then it's prime. So if you find some b and a% b is 0, then it's not prime. So let's say we want to try to write n as a sum of 2 primes. Here's what you do. Start with, some variable equal to 3. If p is prime and n minus p is prime, then you're done. You found a way to write it. N is the sum of p, a prime, and n minus p, which is also a prime. So print out, n equals this thing plus that thing. Okay? Otherwise, p equals p plus 2. Go back and try again. So now we'll set p to 5. Is 5 prime? Yes. Is there a number minus 5 prime? If it is, we're done. If not, set p to 7. Is 7 prime? Yes. Is our number minus 7 prime? Well, if it's not, set p to 9. Is 9 prime? No. Keep going. Set it to 11. Is 11 prime? Yes. Is our number minus 11 prime? Maybe it is. We're done. Our number is 11 plus our number minus 11. Okay? This is probably the fastest way to do this. A slightly worse way is to, just go through all numbers from, 1 to n minus 1 and test both of these to see if they're prime, right? As soon as you know p is not prime, don't bother testing n minus p. Because even if this is prime, if that's not, this isn't a solution. Okay, the slowest approach, and I always see people do this when I give this assignment, is to make a pair of nested loops for I equals 1 to n, for j equals 1 to n. See if I is prime, see if j is prime, see if I plus j is equal to n. Do not do that. That will not finish. Right? Be tactical about this. Generate primes and test to see whether n minus that prime is also prime. All right, so if you're working around 5 million, if you take this approach, you only have to test up to the square root of 5 million. What's that? I don't know. It's around 2,000. If you're only testing odd numbers, that's around 1,000. You're going to have to try 1,000 cases. If you check every number up to n minus 1, you're going to do around 5 million cases. If you generate every number from 1 to 5 million minus 1, generate another number in that range, take all the combinations of those, see which ones add up to 5 million and are both prime, you're going to end up doing 25 trillion different cases. That's going to take a really long time. You can store the numbers that you've already found, but you don't have to. And if you do that, then you got to worry about how much space do I need to store these. So my suggestion is just you know, go from 3 up to the square root of n, see if that's prime, see if n minus p is prime. There are functions you can use that will tell you if a number is prime. Do not use those. Okay, you want to write this yourself. Alright, and I would like this done in C. I suggest running it on the Linux server because that's a standardized environment. And, you know, if you're taking this class, presumably you've taken at least through CSE215 or the equivalent. Go back and look at your notes on that if you're unsure about, you know, compiling C code or testing for primality or things like that. That's stuff you've probably done in the past. If you're not sure how to do this, if you're stuck on getting started or something, come by office hours and we can work through it. Why are we starting at 3 if we have to start at 5,000? I don't know what that means. Can you rephrase that? So you're starting to test Goldbach's conjecture from 5 million, right? Goldbach's conjecture would say, you know, there's a way to write 5 million as a sum of 2 primes. Well, what are those primes? Well, you know, we don't know. But one possibility would be, you know, 3 plus 4,997,997. Well, I know 3 is prime. I don't know if this is prime. So check that and see if it's prime. If it is, you're done. If not, you know, we could write this as 5 plus this number. Well, 5 is prime. If I check this, that's not prime, so that's not going to work. Right? But keep going on. 7 plus, you know, until you find a case where this is prime and that is prime, and then you're done. And then you just go ahead and you print out your answer, which would say, you know, 5 million equals 7 plus, right? Assuming that's prime. I don't know if it is. So we always start checking primes, you know, from 3 on up, even though the number we're checking to see if it can be written as a sum of 2 primes is, you know, 5 million in this case. So 1 is not a prime number. That's by definition. 2 is a prime number. But if you subtract 2 from an even number, you're going to get an even number. And so other than 4 equals 2 plus 2, we're not going to be able to write any other even number as 2 plus a prime. So we don't have to check 2. So you're safe starting from 3 and just checking odd primes. So let's pseudocode a prime number algorithm. There you go. This only works if n is odd. So if n is an odd number, I can start with 3, I can go up to and including the square root of n by 2's, and see if n is divisible by I. If it is, I can stop right there and say it's not prime. If I get all the way through this and I didn't return, then I know it is prime, so I can return a 1. Let's see, but we have to find an even number from adding together two primes we find and then repeat that 499 more times. You want to start with an even number and know if it can be written as P1 plus P2. So generate a prime P1 and see if your number minus P1 is also prime. Don't start generating primes and adding them together to see if they equal n, right? So you know, let's write 100 as a sum of two primes. So I'm going to start with 3 and 100 minus 3 and see if both of those are prime. Well, this is prime, this is 97, that's prime, yeah. So I'm done. Okay, let's try 102. So I'll start with 3 and 100 minus 3. Sorry, 102 minus 3. So this is prime. 102 minus 3 is 99. That's not prime. What part are you confused on? No, it would not. You can do nested loops. Just be tactical in what you're doing. If you run your program and it works for small numbers and starts slowing down and you get up to 10,000 and it's dragging, right? Take another look at your algorithm. You're probably doing something less efficiently than you could. So if I do loops like this, it's okay, but if just iterating over every number, then it's not okay. I don't know if I agree with that or not. It depends what loops like this mean and what you mean by iterating over every number. I'm not going to make a blanket statement like don't do nested loops, but don't do this, okay? Suppose I want to write the number 1000 as a pair of primes, right? Just don't do that. This is going to go through a million combinations of integers, very few of which are going to even add up to 1,000. and fewer of those, in which case I and j are both going to be prime. That's a really, really hard, exhaustive way to do this. It's correct, it will work, but it's going to be really, really slow, right? And if I'm considering one number, you know, I equals 17, I don't need to know if, 17 plus 2 is 1,000. How about 17 plus 3? How about 17 plus 4? There's only one other integer that'll add up to 1,000. That's 1,000 minus I. So see if that's prime, see if that's prime. All right, so how do you structure this? Get your starting number, get the number of things that you want to test Goldbach's conjecture against, right? Make a loop. Let's go through this number of things to do times. Call a function that'll write this number out as a sum of two primes. Go on to the next even number, go back up to the top of your loop. That's your whole main program. All right, this is pseudocode, it's not really C. So you've got a starting number and you want to do some number of tests, right? So just loop that many times. Make a function called try that will take a number and try to write it as a sum of two primes. Call it on start, add 2 to start, call it again, add 2 more, call it again. Do that in a loop, a total of number of things to do times. I get laggy at this point in the afternoon. I think my computer needs a nap or something. Okay, how do we write this try function? How do we know if start is expressible as a sum of two primes? Right? Make a loop. P1 goes from 3 up to start by 2, right? Set P2 equal to start minus P1. If P1 and P2 are both prime, print your answer and return. So it's a pretty tight little loop, right? This is your first number that, could be prime, start from 3, go up by 2, so it's odd numbers. This is, the number you're testing minus that prime, see if both P1 and P2 are prime. So try this on paper with some particular numbers, and I think it might help solidify it. And then, so that's 3 or 4 lines of code, but you need this ability to test whether or not a number is prime. So that's that function that we did a few minutes ago to see if a number is prime. And that's another loop, which, goes from 3 to the square root of n and checks to see if n is divisible by any possible factor. So my suggestion would be start with this. Write a function that takes an integer, tells you if it's prime or not. And then take that function and write this function, which takes an even number and tries to print it as a sum of two primes. And then take that function and put it inside another function that repeatedly calls try with consecutive even numbers. And then that's your 215 programming assignment. So bottom up kind of works well for this. and get started on it, and come by and ask specific questions if questions come up. Let's see, is thorough commenting required like in 222? You need to always comment your code. It's an absolute requirement. It's for the salvation of your soul. No, I'm not going to take off points for not commenting, other than I want your name in your code somewhere. So put your name in there. But, you know, put comments in anyway. It's going to help you. Does it take more memory to call an outside function instead of nested loops? Yeah, it's a little less efficient. But the savings in person power as far as writing and debugging and maintaining code is probably well worth it. And if you're rusty on C, I'd say go back and look at some of your 121 work. Look at some of those assignments. You do a prime number program in there. You do a prime number program at 120 usually too. And see if that helps. Cool. And yeah, don't hesitate to come to office hours. Share your screen, show me your code. We can work on it from there. All right, let's go through homework questions. So someone asked for an example of induction with inequalities, but let's go through a specific questions if you have them, and we can pick on. Or I can make one up. All right, let's look at 351. And then let's look at 358. Oh man, I'm getting like super laggy. So I've got everything closed that I can possibly close. So let me go to my super low res. But you can still hear me, that's good. I should start doing my cell phone reception problem impersonation. All right, so 351, prove n times n plus 1 times n plus 2 is divisible by 3 for all n bigger than or equal to 1. Using mathematical induction. So how do we start this? What's a possible first step here? Write a proposition. Awesome. Let P of n be the proposition n times n plus 1 times n plus 2 is divisible by 3. P of n is not the proposition that this is true for all n. That doesn't make sense. P of n says, you know, if I plug a 1 in here, P of 1 is the proposition that 1 times 2 times 3 is divisible by 3. P of 5 is the proposition that 5 times 6 times 7 is divisible by 3. If I say for all n, then what do I have? P of 1 is the proposition that 1 times 2 times 3 is divisible by 3 for all n bigger than or equal to 1. That doesn't make any sense. Alright? So P of n is a statement about a particular value of n, in particular that this thing is divisible by 3. Alright, so we want to show that this can be written as 3 times an integer. So I would actually phrase this a little differently, using our divides notation. So 3 divides this. So I'm going to write what someone just did in chat, but I'm going to put it off on a sidebar here. What I'm trying to do is show that this is equal to 3 times an integer. And it's that last word, integer, that makes this so interesting. Because I can write anything as 3 times something. I can write pi as 3 times something, right? What's really interesting is that this something can be an integer. Okay, so that's the significant part. Well, if we're going to use a proof by mathematical induction, which is what we're told we have to use, what are we going to need to do? What are the 2 things we need to show? Almost. Those are part of it. Yeah, we need to show that P of 1 is true. And then we need to show the inductive step. We need to show that P of n gets us P of n plus 1. Alright, well let's prove P of 1 since we're here right now. So what does P of 1 say? It says that this number is divisible by 3. Well, 1 times 1 plus 1 times 1 plus 2, that's just 1 times 2 times 3 equals 6. And 6 is equal to 3 times 2. So P of 1 is definitely true. Okay, step 2. Prove that P of n gets us P of n plus 1 for any n bigger than or equal to 1. So now we have a whole new subproblem to do. So I'll start a new sheet. Prove P of n implies P of n plus 1. Alright, so forgetting about, divisibility by 3 and all that kind of stuff, let's just prove this smaller proposition, that if P is true for n, it's true for n plus 1. So what's our first statement in a proof like this? P of n. And how do I know P of n is true? That's the hypothesis. So our next statement, well, P of n is just 4 characters. We can't really do much with 4 characters. Let's spell out what P of n says. Since P of n is true, this means 3 is a factor of n times n plus 1 times n plus 2. And yeah, what we're after is P of n plus 1. So, off on the sidebar, what am I really trying to show? I want to show p of n plus 1. Well, what does that say? P of n plus 1 says 3 divides n plus 1 times n plus 1 plus 1 times n plus 1 plus 2. So 3 divides that. So this is what I'm trying to get to. This is all that I know. So now the trick is, can we write this somehow in a way that gets us to that? So we could write this. As long as I specify that k is contained in the set of integers. Perfect. Well, at this point, start multiplying stuff. So n plus 1, n plus 2, n plus 3. That's n plus 1 times n squared plus 5n plus 6, which is n cubed plus 5n squared plus 6n plus n squared plus 5n plus 6. So that's n cubed plus 6n squared plus 11n plus 6. This is the point where depression sinks in and we start to feel hopeless. Push through it. Okay. We got a lot of things we can write down here, and hopefully some of them are going to work together. So over here on my ignore side, I'm going to say show that n cubed plus 6n squared plus 11n plus 6 equals 3 times, I don't know, some other number j. So question in chat, wouldn't it be true p of n plus 1 equals 3 times k plus 1? So first of all, p of n plus 1 is a proposition. It's an English sentence. So it cannot be equal to an algebraic formula like 3 times k plus 1. But we could try to use the proposition p of n plus 1 to make a statement about something involving 3 times k plus 1. But we gotta be really careful to keep these two things in their proper universes, right? A proposition is a statement. 3k plus 1 is a formula. Something equals something is a proposition. But I think you're smelling the direction we want to go in. So we want to show that this is 3 times something, and we know that this is 3 times k. Let's spell this out. So this is definition of divisibility. This is the definition of p of n. Let's just do some algebra. So n times n plus 1 times n plus 2 is going to be n squared plus 3n plus 2 times n. So this is going to be n cubed plus 3n squared plus 2n. So we know for a fact n cubed plus 3n squared plus 2n equals 3 times k. Now we're simultaneously stuck and at the precipice of a great leap. So we know this is true, and we're trying to show this is true. How do we connect those together? How do we use this to get here? This is the great intuitive leap. So what do you see in comparing these two expressions? Anything that jumps out at you? So if I just look at these, I've got an n cubed and an n cubed. Well, those are the same. I've got a 3n squared and a 6n squared. Well, those aren't the same, but you know, if I added 3n squared to this, I would get this. And 3n squared is divisible by 3, right? It's 3 times n squared. And here I've got a 2n, here I've got an 11n, but you know what? If I added 9n to this, I'd get 11n. And guess what? 9n is divisible by 3. And over here I've got a 6. I don't have a constant here, but guess what? 6 is divisible by 3. So the difference between this and this is feeling like maybe that difference is a multiple of 3. Right? Take this thing, add 3n squared, add 9n, add 6, and you're going to get this. And yeah, it's related to their divisibility by n, right? We have similar terms other than the constant term. And the difference in these terms is each a multiple of 3. So that takes thinking about, but once you have that insight, you can put it together into something like this. So we'll have some magic here, right? And this step 4 was just algebra. And then maybe some magic of the mental type comes in. And now I'm going to write the following statement, which is absolutely guaranteed positively to be true. N plus 1 times n plus 2 times n plus 3 equals n cubed plus 6n squared plus 11n plus 6. And that's not using something illegal, right? I put it in my ignore section because I said this was 3 times an integer, right? And I don't know that, so I can't be part of my proof. But I know this. This is just algebra. So this product of binomials is equal to this cubic equation, which is equal to n cubed plus 3n squared plus 2n plus, what do I have to add? 3n squared plus 9n plus 6. That's just algebra. I can write that down without knowing any of this stuff, right? No one can argue with you that 3n squared plus 3n squared is 6n squared and 2n plus 9n is 11n. So this is still absolutely true, but now I'm going to write that this is equal to, and in place of this expression, I'm going to do 3k. And in place of this expression, I'm going to do 3 times n squared plus 3n plus 2. I'm going to factor out that 3. And now I've got 3 times something plus 3 times something, so I can write this as 3 times integer k plus n squared plus 3n plus 2. And that's algebra with like little magic symbols around it. And what did we just do in that big long line of algebraic trickery? We showed that this n1 plus 1 times n plus 2 times n plus 3 is equal to 3 times an integer. Right? So therefore n divides n plus 1, 3 divides n plus 1, n plus 2, n plus 3. Therefore, p of n plus 1. Therefore, p of n for all n bigger than or equal to 1, mathematical induction, QED. So again, this familiar structure, right? Stuff that we don't really have a whole lot of wiggle room in what we write. And then stuff that, you know, kind of we can recite in our sleep at some point, but usually one step somewhere in the middle that bridges a gap from, like, you know, what's handed to us and what we need to be able to finish this off. And this is subtle, right? This takes fiddling around with. It's the puzzle part of it. It's the let's try this, let's try that. Well, that feels closer. Let's try a variation on that kind of thing. The most important part of this is mathematical induction, right? not being really good at finding these little tricks or thinking about, L-shaped tiles or things like that. That's cool when you can do it and it feels fun, but it's kind of like, puzzle playing. But the lesson here is the principle of mathematical induction and, just seeing examples of its application to different situations. We'll see this with an inequality problem next. All right, questions about this? And then we'll go on to question 8. Yeah, you're welcome. This is my whole game plan today, is just go through lots of induction examples. And the midterm. Alright, let's look at number 8. So inequalities. So number 8 says, prove that n factorial is bigger than 2 to the n for all n bigger than or equal to 4, using mathematical induction. Alright, start with a proposition. Let P of n be the proposition that n factorial is bigger than 2 to the n. And we want to prove P of n for all n bigger than or equal to 4. Step 1, base case, prove not P of 1 here, but P of 4. Well, 4 factorial equals 24, 2 to the 4th equals 16, 24 is bigger than 16, therefore 4 factorial is bigger than 2 to the 4th, therefore P of 4 is true. As usual, plug in the number and see if the proposition is true. And this proposition is not a complex one. We know what factorials are, we know what 2 to the n is, so we could prove P of 100. Find 100 factorial, find 2 to the 100th, and show the inequality. The trick is we're trying to show this for all n bigger than or equal to 4, so we would have to do an infinite number of specific cases to prove this by looking at specifics. So instead of doing that, we're going to use induction. So what's the goal with induction? Prove that if this is true for n, it's true for n plus 1. So same drill as before. Step 1, assume the hypothesis. Step 2, what does P of n say? It says n factorial is bigger than 2 to the n. Alright, what am I working towards? I want to show P of n plus 1, which means I want to show n plus 1 factorial is bigger than 2 to the n plus 1. Okay, we're going to use some properties of integers here that relate to inequalities and multiplication. How do you know that you're allowed to use those? I don't know. I mean, it depends what the context is. If you're in doubt, ask, right? But generally, I'm not going to ask you to prove, that if A is bigger than B, then 2A is bigger than 2B. We take that as a property of an integer. But you got to be a little careful, right? Because you could just say, well, this is obviously true because of properties of integers. Well, maybe it's obvious to you, but, not to the person who asked the question. But if we assume, things that we learned about multiplying integers and preserving inequalities, we can do the following. So how does n plus 1 factorial relate to n factorial? What could we possibly use to connect something here with something there? Yeah, n plus 1 factorial is equal to n plus 1 times n factorial. And how about 2 to the n plus 1 compared to 2 to the n? So n plus 1 factorial is just 2 times 2 to the n. Now, why did I write those? I don't know, because I saw, some factorials here and here, and I saw some 2 to the n's here and here. My brain doesn't say, well, let's try to relate n factorial to 2 to the n plus 1, right? Let's relate the factorial to the factorial. Let's relate the exponent to the exponent, right? I'm lazy, so I'm going for the lowest hanging fruit possible. But this is a really good pair of observations now, because we're trying to make an observation about how this compares to this. And we know from P of n some fact about how this compares to this. If this is bigger than that, and I multiply both of these by 2, then 2 times this will be bigger than 2 that. And if I multiply this first thing by something bigger than 2, that inequality only gets even more extreme. And so if n plus 1 is bigger than 2, right, this inequality is going to be preserved. N plus 1 will always be bigger than 2, right? So these are just kind of, the feelings that one gets when looking at this and thinking about it, that hopefully lead to, some kind of ultimately productive path. So let's start writing this out. So n plus 1 is bigger than 2. And how do we know this? Because n is bigger than or equal to 4. And so n plus 1 will be bigger than or equal to 5, which is bigger than 2. So there's some properties of integers in there, right? And then let's do the following. So n factorial is bigger than 2 to the n. So if I do 2 times n factorial, that should be bigger than 2 times 2 to the n. Right? So that's properties of, that inequality. If you have a is bigger than b and you multiply by something positive, then that thing is still bigger than that thing. But it's got to be multiplied by something positive. All right. And n plus 1 is bigger than 2, and so n plus 1 times n factorial is bigger than 2 times n factorial. And that's more properties of greater than. And I don't know if I would make these separate steps or not. I'm breaking them into lots of separate steps. Well, now n plus 1 times n factorial is bigger than 2 times n factorial, which is bigger than 2 times 2 to the n. And that's just combining steps 4 and 5. And now I'm going to rewrite n plus 1 times n factorial as n plus 1 factorial and say that's bigger than 2 times n factorial. And that's bigger than, I'm going to rewrite this as 2 to the n plus 1. And that's just like algebra. And if this is bigger than that, and that's bigger than this other thing, then this is bigger than that other thing. N plus 1 factorial is bigger than 2 to the n plus 1. That follows from step 7. And that is P of n plus 1. Why is step 3 2? N plus 1 is bigger than 2? Because n is bigger than or equal to 4. Right? So we're trying to prove Pn implies Pn plus 1 for n bigger than or equal to 4. So if n is bigger than 4, n plus 1 is bigger than 5. And then you just wrap it up with the mathematical induction ribbon. Therefore P of n plus 1, therefore P of n implies P of n plus 1. That's the inductive step of mathematical inductive proof, which combined with the base step, which we proved up here, tells us P of n is true for all n. And that's what we were trying to show. So number 9 is another inequality proof that's similar to that. So play around with it, see where you get. And like with other things in this course, generally the more you work with these and the more you struggle with them, the more successful you are at subsequent attempts. All right, let's talk about the midterm. All right, so let's see. Question 1, not a whole lot of issue there. Union of two sets, so that's just 1, 3, 5, 6, 7, 8, 9. Intersection of A and B is just going to be 5 things in common. Then A, take away C, so start with A, throw away everything that's in C. That's 6, 7, 8, 9, so that's also just the set 5. A slash C, it's a backslash, not a forward slash. That's A, take away C, it's a subtraction. It's the complement of C in A. All right, question 2, use membership tables to prove the following. So the complement of A union B is equal to the intersection of A complement with B complement. And so this is De Morgan's theorem. Now generally when you're trying to show something with a membership table, you want to do more than just write this, write this, write this, and show that they're the same. You want to develop your table, right, so that if you make a mistake, you get partial credit. So make a column for A, make a column for B, make a column for their union, make a column for the complement of that column. That shows you what the left side's equal to in all cases. Now make a column for A complement, make a column for B complement, make a column for the intersection of those. And now observe that the things in that column are exactly the same as what you wrote in this column, regardless of whether the element in question belongs to A or B, or both or neither. And once you've observed that, you've proven that this set and this set are the same. A backslash C is the same as A minus C. Yeah, the backslash is a little more formal, but we can think of it as subtracting C from A, and so sometimes you'll see it written with a minus sign. I try to stick to the backslash. Could you do third if we have time? Third what? Second what? I don't know what question you're referring to. Question 2. You mean write out the table? So normally we write true and false to say, you know, this element does not belong to A, it does not belong to B. But since we're engineering CS students, right, we usually write 0 as 1. 0 means not a member, 1 means it is a member. So if something's not a member of A or B, it's not a member of the union. But if it belongs to B, if it belongs to A, if it belongs to both, it will be a member of the union. So there's what our truth table looks like for the union of A and B. And if it does not belong to the union, it does belong to the complement. If it does belong to the union, it does not belong to the complement. So there's the truth table for A union B complement. And then let's write its membership in A complement and B complement. Well, if it doesn't belong to A, then it does belong to the complement. And if it belongs to A, it's not in the complement. And the same for B. And of course, these are just, you know, Boolean equation truth tables, exactly the same as you know, membership tables. So this is all, you know, 250 stuff. And now if we intersect, so here it belongs to both A complement and B complement, so it's in the intersection. Here it doesn't belong to B. Here it doesn't belong to A complement, and here it's in neither of those, so it's not in the intersection. And now we make the observation that this and this are exactly the same in all cases. Any element in the universe that we think of, whether it belongs to B or A or both or neither, right, its membership in this set is exactly the same as its membership in this set. So the fact that these two rows are the same in all positions tells us that these sets are exactly the same. So that's enough to prove that this is true. All right, question 3 was playing around with some propositions. So today is Friday and we have an exam today. Those are the propositions P and Q. Write in words the meaning of the following. I didn't see a lot of troubles with this. So if today is Friday, then we have an exam today. This arrow is always an if then. P and Q says today is Friday and we have an exam today. Not Q implies not P says if we do not have an exam today, then today is not Friday. And then D and E, which some people skipped, I guess because I had some extra words here. D says, you know, today is Friday or we do not have an exam today. That would be written as P or, so, you know, the V symbol, P or not Q. And then if today is not Friday, we do not have an exam, that's like not P, arrow, or implies not Q. All right, name the law of logic or the fallacy for the following arguments. If it rained, then the grass is wet. The grass is wet, therefore it rained. Okay, if it rained, then the grass is wet. The grass is wet, therefore it rained. So is that a law of logic or a fallacy? Right, that's a fallacy. That's the fallacy of affirming the conclusion. It's the same thing as, you know, if the lamp is broken, the room is dark. The room is dark, so the lamp is broken. All right, so part 1, fallacy of affirming the conclusion. If it rained, the grass is wet. The grass is not wet, therefore it did not rain. So if it rained, the grass is wet. The grass is not wet, therefore it did not rain. That is a valid law of logic that's called indirect proof, or proof by contrapositive. right? This has got to be the case, because if R is true, W has to be true, and we're told W is false. So this is indirect reasoning. Third one, if it rained, then the grass is wet. It did not rain, therefore the grass is not wet. And that's also a fallacy. That's the fallacy of denying the hypothesis. Because maybe someone turned on the water sprinklers and watered the grass. If it rains, the grass is wet. It did not rain, but the grass could still be wet. So that's a fallacy. And then the fourth one, if it rained, then the grass is wet. It rained, therefore the grass is wet. That's good old direct reasoning, or detachment. So those two are laws of logic, those two are fallacies. But a few people did not identify the fallacy or law of logic. They simply said true or false for these. And the goal was to, name the law of logic or the fallacy. All right, prove the following with a direct or indirect proof. So not P implies R, not P and Q, Q, therefore R. All right, these are formal proofs. So we've been working on these. We did homework on these. You need to have, a series of propositions. Every proposition has to be true. It should be numbered, and it should have a justification for why it's true. Let's see, 4b, indirect reasoning. 4b is, that is indirect reasoning. Did I take off points for that? If so, I'll go back and give you those points back. Because, yeah, that is the answer for 4b. So I'll take a look at that after class. All right, so we want to prove this theorem. So let's look at a direct proof. So let's start with some hypotheses. Not P implies R. And I'm going to say not P and Q. So that's a hypothesis also. And then I'm going to throw De Morgan on here and say not P or not Q. Why? Because De Morgan's always fun. Well, we also know that Q is true. That's a hypothesis. And so there's a law of logic. I think it's disjunctive simplification, but I could be wrong. I'd have to look it up. But it says, if this or that is true, and that thing is false, then this must be true. So we can put 3 and 4 together and come up with not P, and I think that's disjunctive simplification. But I don't have page 58 and 59 handy. And then this goes together with proposition 1 to get R. And that's detachment. 1 and 5. And that's what we were trying to show. Now if you want to do an indirect proof, let's start off with not R. That's the negation of the conclusion. And then, I don't know, I'm going to do not P implies R. That's a hypothesis. And I picked that one because I can put these together and not P implies R, but R is false, and so that implies not P. That's indirect reasoning. Applied to 1 and 2, and so that means P is true. That's, double negation. And I also know Q because that's a hypothesis, which means I have P and Q, and that's statements 4 and 5. But I also know not P and Q, and that's a hypothesis, and that's enough to say contradiction. And I'm okay saying contradiction right there. Because here I wrote a proposition, and here I wrote the exact same proposition, but with a negation in front of it. So I'm not asking the reader to, you know, apply De Morgan's theorem or distribute an operator or something like that. These two directly contradict each other. Therefore, R must be true. And that's what we were asked to show. All right, question 6, short true-false questions about division and divisibility. So is 17 congruent to 1 mod 2? Yes, they both have a remainder of 1 when divided by 2. Easy way to check congruence, right? A is congruent to B, modulo M, if and only if M divides their difference. So for all of these, we can say 17 minus 1 is 16. That's divisible by 2. So yes, those are congruent. 17 minus 2 is 15. That's divisible by 3. So those are congruent. 17 minus negative 1 is 18. That's divisible by 3. So those are congruent. Put differently, this is 1 less than a multiple of 3. This is also 1 less than a multiple of 3. Because 18 is a multiple of 3. 6 divides 24. Yes, that is true. 24 is 4 times 6. And then the division algorithm is a computer algorithm for dividing large integers. No, the division algorithm is a theorem stating that there's a unique integer r such that you can write m as a multiple of q plus r, where r is less than or equal to q minus 1 and bigger than or equal to 0, blah, blah, blah. It's a big, long theorem. It has nothing to do with an algorithm or with dividing large integers. So this one is false, but these other statements are all true. And then finally, question 7. Prove that the sum of two even integers is even using the definition of even and odd. Again, if you have the right idea, that's good. That means you have what you need to write this proof. But the whole point is writing a formal proof. And if you write something about, each integer is 2 times something, when you add them, you get 2 times something else. Yeah, that's the inspiration, okay? That's the aha. I know why this is true, right? The challenge is, how do you write a proof to demonstrate that? So it's almost all about the presentation, right? Although you have to, know what it is that you're going to write up. Isn't the theorem implemented in computer algorithms? What theorem? The division algorithm is the name of a theorem. I mean, we could write a computer program that does something related to the division algorithm, just like we could write a computer program related to Goldbach's conjecture. But we wouldn't say Goldbach's conjecture is a computer algorithm for testing even numbers. Right, and when we went over the division algorithm, we actually commented about the fact that it's not an algorithm at all. It's really a theorem, but it's just called an algorithm. And in particular, it relates to the existence of a unique modular number. So the basic setup is, if I take the number 25 and I take the number 7, I can say 25 equals something times 7 plus something else. The division algorithm states that I can write this uniquely such that this thing is bigger than or equal to 0 and less than 7. And that's the real punchline of the division algorithm, the fact that there's always a way to write it like this, and the way you can write it is unique. So that if we restrict our attention to remainders that are strictly non-negative and smaller than what you're dividing by, we get a unique remainder for any pair of integers like this. And that's why we can do all the things that we've done and will do with modular arithmetic. All right, prove that the sum of two even integers is even. prove that the sum of two even integers is even. I'm abbreviating and using symbols. All right, so step one. So let me phrase this in a better form. Prove that if a comma b are even, then a plus b is even. All right, so step one, a is even. That's a hypothesis. Step two, b is even. That's a hypothesis. Step three, a equals 2k, where k is an integer. That's a definition of even. Step four, b is equal to 2 times j, where j is an integer. That's also a definition of even. Nobody used the same j and k here, which was awesome. That's like such a battle for me usually, and this class has totally nailed that. So we've written a and b as each 2 times some integer. We're trying to show a plus b is even. Same thing we've done before, add them up. A plus b equals 2k plus 2j. And I can factor out a 2 times k plus j, and that's just substitution. 3 and 4 and algebra. And now we're basically done. I've written a plus b is 2 times something. A plus b is thus even. Definition of even, and that's what we were trying to show. So if you're not sure about this, try writing up some proofs and come by office and let's go through them, right? And if you're missing a step, if you're doing something in a different way or something like that, right, I can tell you in office hours instead of on an exam or a homework. And if you keep working on this, you will figure it out, right? And as I've told some people, you know, this is for some people, you know, a kind of first treatment of formal proofs. This is not a deal breaker for being a computer scientist, right? This is something that develops over time. It's something you'll encounter in other courses, you know, typically at a university. And it's something that, you know, each time you encounter it, it will make a little more sense. It will come a little more quickly and so on and so forth. But there will be proofs on the final exam. So if you're confused about this, I would say, you know, keep working on some of these problems and come by office hours and let's sit down and go through, you know, what you've got and figure out if there's issues with it, and if there is, talk about, you know, what those issues are and what could be changed. And once you get it right, you'll know you've got it, and it's a much more comfortable place. But it takes struggling to get there, right? But you know, we can definitely work through that. All right. So finish up your homeworks. Friday we will do some wrap up on induction. Talk about a few last cases of it, and start talking a little more about recursive algorithms, recursive functions, and how that ties into induction. We'll look at towers of Hanoi, and that will probably wrap us up for induction. And then next week we'll go on to start talking about counting. So that'll be our next topic. And we are flying through this quarter. So this is week 7 already. So good things happening. All right. Have a good rest of the day. I will see you next time. Thank you.